Okay, I'm going to take GeoGebra here and graph a unit circle on it. So I'm going to put the point 0, 0. I'm going to put the point 1, 0. Shut up. And now I'm going to graph a circle. There we go. Okay. Everybody agree? A nice unit circle. You're a little off. All right. Let's put a point on here now. Okay. So that point is stuck to the unit circle. No matter where I move it, it's on the circle. Let's grab this perpendicular tool. So I'm going to make a line that goes through this point, but is always going to be perpendicular to the x-axis. That didn't work. Let's try that again. I got to get the point, not the circle, the point. Point, x-axis. What is going on? X-axis, point. It is being glitchy, isn't it? Select point. There we go, and perpendicular line. All right. So now, no matter where I move that point, that line will go through the point, but will be perpendicular to the x-axis. And really, the whole purpose I did that is so that I can now mark where that line intersects the x-axis. And that's really all I wanted it for, so let's make it go away. So now I will have that point on the x-axis directly above or below my point in the unit circle, right? Pretty cool. The reason I did that is because I want to now draw our reference triangle for whatever angle is created. So now, there's a quadrant 1 reference triangle, quadrant 2, quadrant 3, quadrant 4. Agreed? Okay. Now, I'm going to take this line segment down here. Let's right-click it, and I'm going to make it a special color. First of all, what trig function does that segment correspond to? This segment. Cosine. Now, this is going to be a psychological experiment. Everybody close your eyes, clear your brain. Like that. What is the first color that comes into your head?
Yellow.
I got the weirdest students this year. I would say in years past, 80% would all say blue.
Oh yeah, I like blue.
But now, every year, everybody's saying like these obscure, weird, random, like. If you don't think blue when you think cosine, you're crazy. That's all I'm saying. Cosine is clearly blue, and sine is clearly red. Absolutely red. Okay. Now I'm also going to mark this angle right here. Beautiful. Okay?
The hypotenuse has got to be...
The hypotenuse is not a trig function, so I don't even care what it is. In fact, usually I don't even show it.
Such an interesting color.
We don't even need it. Okay. So here's our unit circle, and here's our sine and cosine. As we start learning the graphs of tangent and secant and cosecant and cotangent, I will actually show line segments representing them on the unit circle as well. It's pretty cool. But for now, here's a unit circle simulation showing sine and cosine for various angles. Now what we want to focus on today is this relationship. If I have the equation y equals sine x, I want to study a little bit today what is the relationship between x and y. If y is equal to the sine of x, x being the input, y being the output, so we're graphing the function sine, how exactly are they related? So the key thing is, I need to go back to my simulation and ask myself, what is representing x in my simulation, and what is representing y? So in this GeoGebra simulation, what would you look for to see what the value of x is? Okay, look at the equation, y equals the sine of x. X is the input of sine. So what in this picture is the input of sine? Here's a hint, its color is green. the angle. That angle is the input of sine. 40.524 degrees. Okay? That is your input. So the angle. Now what is the output of the sine function, which is the y variable? Here's a hint. It's red. The red, right? Isn't that how the unit circle works? Whatever your angle is, your input isn't the length of this output, the sine, right? Okay? So what I want to look at is, how does the length of this line segment change? Now keep in mind, line segments are actually always positive, right? The sine can go negative. So whenever this line segment's above the x-axis, whatever its length is, sine is the positive of that number. If this line segment is below the x-axis, whatever sine is, it's the negative of that number, okay? The reality is, that probably a better definition is the y-coordinate of this point, not the length of the line segment. But we can look and see the size changing. So I want to know, as I increase the size of the angle, what's going to happen to sine? So let's start with an angle really close to 0. Okay, or exactly 0. How long is that red line segment for this? 0. It's 0. So the graph of sine is going to start at the point x coordinate 0, y coordinate 0. As my angle increases, what's going to happen to the length of that red line segment? It's also going to increase. As the size of my angle approaches 90 degrees, what's the length of that red line segment approach? 1. But the minute I hit 90 exactly, and it hits 1 in length, it starts to go back down. So as my angle increases past 90, the length of the line segment comes down. As my angle approaches 180, what does the length of the line segment approach? 0. It then goes negative and starts to approach -1 in length. So as my angle approaches 270, the length of the line segment approaches -1. That's the very smallest it ever gets. It starts going back towards 0 as my angle approaches 360. Once my angle hits 360, the length of the line segment hits 0, and the whole cycle starts over again, and the graph just starts repeating itself for angle measures larger than 360. So here it'd be 270, and you know, 1080, and so on and so on and so on. Make sense? What do we call that when a function absolutely repeats itself every so many? Do you remember what the name was? It was a periodic, right? So we can see the graph of sine is clearly going to be a periodic function because every 360 degrees or 2 pi radians, it just completely repeats itself. Now here's the thing. Is the unit circle a graph of sine? No, it's not. The unit circle is a graph of all points that look like this: cosine of the angle, comma, sine of the angle. I want to know, what do points of the form theta, comma, sine theta look like? Won't that be what the graph of y equals sine x looks like? If whatever your input is your x-coordinate, and then whatever sine outputs is your y-coordinate, that's going to be the graph of sine. So let's use GeoGebra to do this. I'm going to go to my input bar at the bottom. I'm going to create a point. And I'm going to create a point whose x-coordinate is the measure of that angle. Okay? So I have to find out what GeoGebra is calling that angle. Of course, it won't tell me. Okay, they're calling it alpha. So for the x-coordinate of this point, I'm going to say alpha. It always does that. Okay, so I'm going to create a point whose x-coordinate is this angle. Now, GeoGebra is showing us this angle in degrees, but the reality is it's going to use radians when we actually graph this. Okay? So we've got alpha as the x-coordinate, and for the y, I want this new point I'm showing to have the same y-coordinate as this point. And so I believe GeoGebra is calling this point C, capital C. So I'm going to say I want the y-coordinate of capital C. I know it's real small down here, but can you see my code?
Yeah.
there's this y function built into GeoGebra. It takes a point as an input, and it just outputs the y coordinate of that point. So the y coordinate of this new point I'm creating will be the same y coordinate as this point. So right now, if we look, 58 degrees, that's really close to 1 radian. So I predict when I hit enter, you're going to see a point appear right here where my finger is, right there. Right? You bet. See if it's dry right there. Oh, that was awesome. Right? Okay. So that point has an x coordinate of just slightly more than 1 radian. Right? In fact, 1.018, a little bit more than 1 radian. Approximately how many degrees is a radian? Do you remember? It's like 57. So 58 is a little bit more than 1 radian, and the y coordinate's exactly the same, 0.851, 0.851. Okay? If I grab this point and make the angle bigger, where's this point going to go? It's going to go to the right. If I make the angle bigger, isn't the x coordinate of this point the angle? You're going to see this point move to the right, but it's also going to go up a little bit because it's going to have the same height as that point. Okay, you ready for this? Okay, there's an angle close to 0. As you increase, the point moves to the right and starts going up. Here's the very highest the point will ever get, starts coming back down, hits the x-axis, goes negative, okay, and so on and so on. Now the cool thing is I can right-click it and tell GeoGebra to trace it. Okay? Make sense? And so what you're looking now here's one of the bad sides of GeoGebra. Every time I do one complete circle, the angles start counting over again, don't they? So I can't actually rotate this thing around 3 times to represent an angle in the thousands. Okay? It just doesn't work like that. But the reality is, what does the actual graph of sine look like? It's this exact shape repeated over and over and over again in both directions, positive and negative, forever and ever and ever. And in fact, I can actually tell GeoGebra, graph y equals sine of x. And you can see it goes through those points perfectly. Right? So there's your graph of y equals sine x. Make sense? Now the question becomes, all right, that's great. One of the things you're going to have to do on this Friday's quiz is graph that thing 100% accurately by hand, no calculator or anything. So let's start looking for some points that might be really easy points to look for on our coordinate grid. Do you see any points where this graph goes perfectly through an intersection of our grid lines? 0, 0 for sure. What else? 1.51. Yeah, but it doesn't go through 1.51. It goes through pi halves, comma 1, right? Don't we have it memorized in unit circle? Pi halves has a sine of 1, a y coordinate of 1. But pi halves is slightly larger than 1.5. So that's not a perfect grid line. Looks like it goes through 0.5, 0.5, but it really doesn't. What is the nice angle that has a sine of 1/2? Think of your unit circle. What angle has a sine of 1/2? Not pi 4. Pi 6, which 3 divided by 6 is 1/2. Pi is close to 3, so it's really close to 1/2, but it's not quite there. Besides 0, 0, do you see any other points on this graph that show up at nice intersections of our grid lines? None. None. And so this is one of the first functions ever that we are going to accurately graph by hand that we're not going to be able to use nice whole number intervals on our x-axis. We've got to come up with something else entirely. Okay? So the question becomes, how am I going to break up my my grid lines? If I don't go by ones or 1/2s or 1/4s or 1/8s, these really nice consistent intervals, how am I going to do it? Pi's not a bad idea. I wrote up some Mathematica code today. Like 10 minutes. Look, it's not very much code. Okay, so here's our typical grid line. Here's the graph of sine x. Okay, again, this does not cross, besides 0, 0, it doesn't cross anywhere nice.
Anywhere.
Okay. Ever. Never. In fact, that's the definition of an irrational number. If you have your grid lines divided up in rational size intervals, and the period of sine is an irrational number, they will never coincide, ever. Okay? Have you ever heard of, well, here's a stupid question. Have you ever heard of an old Greek dude named Pythagoras?
No.
Okay. Pythagoras was involved in a group, almost a cult really, called the Pythagoreans. Okay? And the Pythagoreans were a little bit crazy about their math. To them, like, their math was almost spiritual, and numbers had like these special meanings to life, right? And one of the things they believed in was you could take any two lengths, and just by repeating them end to end a number of times, you could get them both to be the same length. For example, if I have something of length 14, I have something else of length, I don't know, 21, then I can find a certain number of these 14 length items and a certain number of these 21 length items to where they ended up being the same length. What's 14 times? 42. You can both make them equal 42. If I take 2 of the length 21s and 3 of the length 14s, they both come out to 42, right? Well, one of the Pythagoreans discovered a new number, and he claimed that no matter how many times you took that number, you could not find a common multiple with the number 1. And that number was square root 2. So he discovered square root 2. Basically, what he did was he took a 1 by 1 right triangle and said, whatever the length of this side is, he didn't really know what it was. They didn't know the concept of irrational numbers. He just knew whatever the length of this hypotenuse is. If you take a line segment of length radical 2 and a line segment of length 1, no matter how many multiples of this one you take, and no matter how many multiples of this one you take, you can never make them line up entirely. But the Pythagoreans thought no matter what two numbers you pick, you could always make them coincide. And so this completely disrupted everything the Pythagoreans had believed. So they killed him. The rumor is he made this discovery while at sea and they threw him overboard. Yeah.
But you know he died.
But essentially, I don't know, yeah, he could be a great swimmer out in the
Because they were Greeks, so they could have
Mediterranean. Yeah, you're right.
been short.
So,
Very far.
yeah, the Mediterranean's just a small little lake, basically. But basically, this guy what he discovered was irrational numbers. He was the first person to acknowledge this concept of an irrational number. Fascinating. But yeah, for that reason, you will not find a common grid line crossing in this graph. So what we want to do instead is find nice grid lines. And so what I've come up with is my own way. Are you ready for this?
No.
Oh, what?
I like the red.
Oh, I know what it is. There we go, that's beautiful. Much better grid. Now there actually is a bug in my code. I didn't notice until I'll have to search it out. I don't know what it is. But that's a much better, look at these grid line intersections where this graph is going through.
Oh, yeah.
All of these. How perfect is that, right? And these are all grid line intersections that we are familiar with because we have memorized the unit circle. So look at the X grid lines I selected. Pi 6, pi 4ths, pi 3rds, pi halves, 2 pi 3rds, 3 pi 4ths, 5 pi 6, pi, 7 pi 6, 5 pi 4ths. Oops, I'm missing 4 pi 3rds. Little glitch in my code. But look at the y-axis. I have 1/2, radical 2 over 2, radical 3 over 2, 1. And so look at how sine grows. Pi 6, 1/2. Pi 4ths, radical 2 over 2. Pi 3rds, radical 3 over 2. Pi halves, 1. 2 pi 3rds, radical 3 over 2. 3 pi 4ths, radical 2 over 2. 5 pi 4ths, 1/2. Pi 0, 7 pi 6, negative 1/2. 5 pi 4ths, negative radical 2 over 2. 4 pi 3rds, negative radical 3 over 2. 3 pi halves, negative 1. So the glitch has to be in this code here. Has to be. Yeah! All right. Right? Still don't know why. I mean, I know what I did to fix it, I just don't know why the original wasn't working. Yeah, I do. All right. Square that. Okay. Right? Also, negative pi 6, negative 1/2. How many of you look at this and you kind of understand the unit circle better? Right? For a lot of you, the unit circle is going to be easier to remember now that you've seen this graph and you practiced graphing this a couple times. Okay? So let's draw our own by hand. Okay? Here's some beautiful graph paper. What you're going to want to do is you're going to want to take your own graph paper and you're going to essentially want to go up by pi 12ths. It's just you're going to skip a pi 12th every once in a while. So notice I didn't actually draw a line at pi 12ths, so maybe skip your first grid line on graph paper. Make the second one 2 pi 12ths, pi 6, then pi 4ths, then pi 3rds. Skip 1 and go to pi halves. Skip 1, do 3 in a row, right? Then for your y-axis, I'd probably go up by like maybe quarters, 0.25, 0.5, 0.751. And then you're just going to have to eyeball where radical 2 over 2 is and radical 3 over 2 is. There is no nice way of dividing that up. Now the reality is, when we start graphing these by hand, I'm not going to make you graph all of these points. There's going to be just a set of important ones that make it a lot easier to graph. But for now, I want to draw a really accurate graph of sine. So everybody, with your massive knowledge of the unit circle, what is the sign of 0? Nope. What's the y coordinate at 0? 0, so that's the point 0, 0. Okay, the number I ask is the x coordinate, the one you respond with is the y coordinate. So what's the sign of 0? 0. I can, don't want to. Guys, stop being purposely obnoxious. It's really starting to drive me nuts. What is the sign of pi 6? One half. So I'm going to put a point at pi 6 comma 1/2. What is the sign of pi 4ths? Radical 2 over 2, or you can't really see because the numbers got all jumbled together, but mathematically calls this 1 over radical 2. Same thing as radical 2 over 2. What's the sign of pi 3rds? Radical 3 over 2. And what is the sign of pi halves? 1. So you can see as you move from left to right, the rate at which your y coordinate moving is substantial, but as you move from left to right, it starts slowing down, right? It is actually the same exact graph you would get as if you're measuring a pendulum. When is the pendulum at its fastest velocity? At the very bottom. And then as it approaches its extreme maximum distance from center, it slows down, stops, and changes direction. Same exact thing here. In fact, sine is the exact graph of what a pendulum swinging looks like. Here's your maximum velocity, right? As x increases, y increases the most right here. But it slows down as you approach that extreme end, change direction, and starts accelerating down. So sine of 2 pi thirds is radical 3 over 2, sine of 3 pi fourths is radical 2 over 2, and sine of 5 pi 6 is 1/2, sine of pi is 0. What in the world? And so that is one complete cycle of what sine looks like. We should go in the negative direction as well. I'll zoom out on this when I'm done. Okay, and then say what now?
Is there like one line that skips on all the quadrants, but there's the first line to the
We have a vertical line for every single angle we have memorized on the unit circle. Right? Because the reality is, on the unit circle, we have 30, 45, and 60, but it's almost as if we're skipping 15 and skipping 75.
Oh, I see.
Does that make sense?
Yeah.
And so those would be why we see gaps every once in a while in our vertical lines as well. All right. I do want to go ahead and write this homework down, but we're clearly not finished with this lesson, but you should be able to do a lot and get started with that.
Everyone's out of the room now.
I don't care.